Guys, welcome. Okay, so this first video is going to be 10 minutes long. Hopefully I can reach 10 minutes and get everything done. It's going to be over chapters 1 and 2. Forgive me, I'm going to have to move kind of fast, talk kind of fast, because I want to reach in 10 minutes chapters 1 and 2. Okay, so 4 types of reactors. Okay, so the first one is going to be batch, and then the next one is CSTR, next one is PFR, the next one is PBR. Okay, so let's start with batch. So for every one of these reactors, you have to come up with a material balance. Everything's based on the material balance, and it's also going to be based on the reaction rate. So let's discuss reaction rate first, because that's going to be plugged into the material balance. So you're going to be given this, disappearance of A. That's what that negative RA stands for. It's going to be a constant times C of A. In this case, it's first order. However, you could be given stuff like second order. You can be given kind of a mix reaction rate, depending if you have two reactants. In this case, let's put it like this. That'd be something like A plus B goes to form C plus D. You can be given a lot of weird stuff. You can be given, I don't know, something like this. I don't know, I just made that up, but I've seen some stuff similar to that. So, although you have different reaction rates, it's going to be very similar. If you do the material balance right and you plug in RA into the material balance, it should work out. Just know your calculus and all that kind of stuff. We should see more examples in the future. Okay, so material balance, and this is for a batch reactor. So let's do a brief overview. A batch reactor is a rigid volume, meaning volume is equal to constant, like this, where the volume isn't going to change. And our material balance from intro to processing goes like this. In minus out plus the generation term. You don't have to deal with consumption term because generation will account for that with negative signs. Okay, so from time equals 0 to time equals final, or whenever you stop the reaction or open up that lid, over here would be the lid, this equation applies. So there's nothing going in a batch reactor because you're not putting anything in as the reaction's going. Same thing with out. So you're left with just this guy. Okay, so now we got to plug in terms for these two material balances. You got to plug in one for the generation term, one for the accumulation. Well, generation, that's the weird one. It's basically RA times V. The units of reaction rate are going to be moles over seconds, meters cubed every time. So if you times that by RA by volume, you're going to get rid of this guy because meters cubed is your volume times it, and you get a rate, moles per second. And that kind of agrees with the accumulation term. How much is accumulating per unit time? Okay, so we know it's RAV that goes in for generation. Now for accumulation, this is where you're going to get your differentials in there. It's going to be the change in the amount of A, which is NA, DNA, right? DT. So that's what you're going to plug in because it's a change in A over change in time. Now, let's put everything in. RA times V is going to be equal to D, NA, over DT. So this is what you got. So can we solve that, right? Well, you can't do anything until you substitute in what you got for RA. So I'm just going to assume we have first order, like what we discussed up here, right? So let's say first order, that would give you something like this. And in the problem statements, they're going to specify whether it's first or second order. It's basically the same thing. You're going to plug it in for RA. Well, that's negative RA. So how about we make that positive RA and we say negative KCA. Now you got something you can work with. So you got negative KCA V is equal to DNA over DT. Now, in order to solve differentials like this, you got to have on one side of the equation, you're going to have NA, or you're going to have DCA. In this case, we're going to aim for DCA, and you'll see how it works in a minute. So negative KCA. Here's the trick. You say D, I'm going to put NA here. I'll do it, in two steps rather than one. But you're going to have 1 over volume because I divided volume to the other side over here. Okay, so now what you got is negative KCA DNA over DT over 1 over V. So now you got negative KCA, and it's known that if this is constant, you can move that into the derivative on the numerator. Meaning, you could say, okay, well, DNA over V over DT, which is going to give you DCA over DT. Okay, now what? Now that was the hard part. That was the little non-intuitive step. That's kind of the puzzling part of it. The rest of it's easy. KCA is equal to DCA dt, separable differential equation. moving dt to the other side, and moving ca to the other side under dca. So let's do our integral. So let's get rid of the differentials, right? So this is dt. K was constant, so it came out of the integral from 0 to time. Now, agreeing with these boundaries, we can make the boundaries for the other guy. So this is from your initial concentration, C subscript A naught, Ca. This is at some time later. This is at T is equal to 0 seconds, like right when the reaction starts. So this could be easily solved. You could go, okay, Kt is equal to ln Ca over Ca naught. So now we got rid of differentials, and usually what they're going to ask you is what's the concentration sometime later? Well, let's remove natural log. We could do that by e to negative kt, making both sides the power of e. Well, then e to the ln Ca naught. Well, ln and e cancel. Basically, what you're left with, Ca over Ca naught. We're solving for Ca because that's sometime later. So the concentration, and this is not times t, as a function of t, it's going to be equal to Ca naught e to negative kt. Sorry. Messy. So, let's circle this. That's the equation you work with. They'll give you a time. They'll say, what's the concentration later on if you have an initial concentration of so and such. And this equation is going to change based on your RA. Now, we use first order. The calculus gets a little different when you do K Ca squared, K Cab, or K Cab, CACB, sorry, over Ca plus Cb. You know, all those reaction rates can make this equation different, but the principle is the same on how you get it. Okay. I'll do continuous stir tank reactor right now for the material balance. And here's what it looks like. Let's say it's a batch reactor box type thing. But what you have is you have an inflow and you have an outflow. Like this. Alright, I'm running out of time, guys. I'm going to go to the next video.